Thank you. Thank you for your kind attention, kind introduction. My name is Osamu Takakuwa from Kyushu University, Japan. And today I'd like to talk about our research framework of hydrogen-assisted or hydrogen-assisted particular growth in gaseous hydrogen environment from the viewpoint of the thermally activated hydrogen dislocation interaction. So the dramatic acceleration of particular growth manifests in various metallic materials as shown here, but it still reminds of the considerable consent to both engineering and scientific research field, but there have still been under debate because the phenomenon is so complicated, strongly dependent on the environmental, mechanical, and metallurgical conditions. But one thing I can say for sure is the presence of hydrogen drastically changes the collective plasticity during a particular process, which triggers the severe acceleration of macroscopic particulate growth in various metallic materials. So we have continuously studied on this topic by performing the several particulate growth testing with the control of the gas temperature, gas pressures, and loading frequency and stress intensity factors so as to make it possible to the basic mechanism from the viewpoint of the hydrogen dislocation interaction. So we found the collective plasticity is drastically suppressed in gaseous hydrogen environment. And as you can see, the fatigue crack goes straight away around without severe plastic deformation and crack weak. So we were so interested in why the presence of hydrogen suppresses the plasticity during fatigue process. So this is the motivation of our series of experiments. So some peculiar phenomena of hydrogen-assisted particular growth have been reported here: pressure dependence, temperature dependence, and loading frequency dependence. Looking at the temperature dependence, the higher gas temperature generates the lower the acceleration of particular growth for all stress intensity factor range at constant gas pressure. Also, at frequency dependence, the lower the loading frequency causes the lower the acceleration, even in the higher gas pressure up to the 10 megapascals. So this phenomenon should be time scale behaviors. From the viewpoint, we can discuss the basic mechanism from the viewpoint of the thermally activated process of the hydrogen material interactions, such as hydrogen dislocation interactions. So anyway, when increasing the temperature, the hydrogen concentration at lattice site, the lattice site occupancy increases. But in contradictory to this, the trap site occupancy decreases because the hydrogen atom is more activated at the higher temperature, especially in the lower gas pressure range. So we thought the basic mechanism of hydrogen-assisted particulate growth can be understood more comprehensively by focusing on the temperature dependence and loading frequency dependence from the viewpoint of the thermally activated process of hydrogen dislocation interaction around the crack tip. So this is the motivation of our experiment, our studies. The material tested in this study was low carbon steel with 60% carbon, which had typical ferrite pearlite microstructures. And we performed several particular growth tests using the CT specimens in the nitrogen gas and hydrogen gas with a pressure of 0.7 megapascals. And this presentation will show you a part of experimental results acquired by delta K constant test at 30 megapascal square meters, with changing the loading frequency from 0.01 hertz to 1 hertz for the various temperatures from room temperature to 423 Kelvin, 150 degrees C. So this figure shows the loading frequency dependence of relative acceleration rate of fatigue growth for various temperatures at constant delta K, 30 megapascal square meters. So first of all, looking at the data acquired at 300 Kelvin in temperature here, no loading frequency occurred with a constant value of relative acceleration rate around 35. But at highest temperature, we found a critical loading frequency dependence. The other temperature generated the apparent loading frequencies as well. At highest temperatures, the acceleration rate of 7 became down to the 1.8 by decreasing the loading frequency from 1 Hertz to 0.01 Hertz. So this value 1.8 means the fatigue crack growth rate is very, very close to that in nitrogen gas. So almost no acceleration occurred in this case. So these results, including the temperature frequency and loading frequency simultaneously, are so important for interpreting the mechanism of hydrogen-assisted fatigue crack growth from the viewpoint of the thermally activated process. The EBSD characterization results made on the cross-section of the CT specimens are shown here for the highest temperature with different loading frequencies, as well as the lowest temperature, 300 Kelvin room temperature, together with their acceleration rate here. So the high GROD value around the crack wake became apparently shrunk along with increasing the acceleration rate. And also these fatigue crack pathways at straight part with extremely low GROD value was parallel to the 001 plane analyzed by the two plane tracing methods. So this tendency is very similar to our previous studies. So by comparing the different loading frequencies at highest temperature, you can find the apparent difference between them. So the loading frequency affects the crack propagation fashion in the gaseous hydrogen environment. But I confirmed that the loading frequency did not affect the fatigue crack growth rate in nitrogen gas. So to discuss in more micro scale, the ECC images are shown here. In the images for nitrogen gas and hydrogen gas at highest temperature with lowest loading frequencies, severely developed deformation substructures generated over a wide range from crack wake, so-called subgrains, which is formed by a grain subdivision. So these subgrains is one of the evidences of the occurrence of the severe plasticity during fatigue process. So in those cases, the fatigue propagated accompanied by the severe cyclic plastic strain during fatigue process. When increasing the loading frequency to 1 Hertz, the region with subgrains became shrunk just around the crack wake. And you can see the dislocation cell structures surrounding the subgrain regions. Also, when decreasing the temperature to room temperature, which causes the maximum acceleration, no such developed substructures are generated. So fatigue crack propagated without any intense and extensive plasticity during fatigue process. But when discussing the difference in the deformation substructures, we should pay attention to this fact that this difference comes from different factors. One is the intrinsic hydrogen dislocation interactions. I mean, the hydrogen segregates around the dislocation cores forming the atmosphere, which work as a resistance, strong resistance to dislocation motion. The other is the different fatigue crack growth rate generates the different cumulative plastic strain ahead of the crack tip. So a location is subject to the different number of loading cycles when fatigue crack growth rate is different. So we should pay attention to this fact. But it is quite likely that the hydrogen drastically changes the plasticity during fatigue process. And its effect is strongly dependent on the temperature and loading frequency. So to discuss our series of experimental results, I have to introduce a nice numerical simulation result performed by Professor Matsumoto, sitting here, sitting there. He studied on the interaction between the hydrogen and edge dislocation in BCC ion at different temperature and different dislocation velocity by long time scale molecular dynamics. And in his calculation results, the hydrogen atmosphere strongly pins the dislocation motion, and unrealistic, very, very high shear stress is needed to overcome the hydrogen atmosphere at 300 kelvins, regardless of the dislocation velocity. But at higher temperature, 400 Kelvin, the shear stress to overcome it is much, much lower than the 300 kelvins, and especially in the lower dislocation velocities. So this result indicates the higher temperature with lower loading frequencies generates the lower the magnitude of the accelerations. So now we try to discuss the overall hydrogen-assisted fatigue crack growth aspects from the viewpoint of the breakaway events of dislocation from hydrogen atmosphere. There is breakaway probability that a dislocation can overcome the atmosphere is given by this Arrhenius type equations. And by reference to the Rose's work, EC includes the binding energy multiplying the trap site occupancy. This trap site occupancy can be calculated by the Markov-Foster equations. And I confirmed that the hydrogen trapping, detrapping state can be regarded as a almost equilibrium in the loading frequency ranging from the 0.01 to 1 Hertz. So I can use the trap site occupancy in equilibrium states given by this equation with that side occupancies. So now we can define the experimental equations with the breakaway probability. This term, 1 minus P break, means the probability that dislocation cannot overcome and triggering the intense acceleration of fatigue crack growth. The curves for each temperature represents the fitting data to this experimental equation. So from these fitting results, that we can understand the overall aspects of the hydrogen-assisted fatigue crack growth at several temperatures and loading frequencies from the viewpoint of the breakaway events of dislocation from hydrogen atmosphere. But I think this concept is probably able to be applied to the case with different gas pressure. So now I'd like to summarize my presentation with some schematic illustrations of the 4 cases with different temperatures and loading frequencies with their crack chip plasticity. Thank you for your kind attention.
Thank you very much.